Hello, this is Dr. Stutzman, and today we're talking about finding solutions to differential equations for special kinds where we have separable differential equations. And we'll talk about what separable means. So our goal in this today is to find a specific kind of differential equation to solve, which is separable. Because in general, differential equations are not easy to solve. And that's why there's courses you might be taking after Calc 2, which are about different differential equations technique. And you can get to call differential equations something really cool like diffie-qs. So what a separable differential equation is first order, which means I only have the first derivative. And it can be written where dy dx is some function of x times some function of y. And the reason why it's separable is that I'm going to divide, put f of y on one side and put the dx on the other side. And I can manipulate it just so each variable shows up on one side of the equation. So if f of y is not equal to 0, I can make f of y being the reciprocal of 1 over f of y. And if you move things around, I get h of y dy equals g of x dx. And what you notice once we did this is that I can now take the antiderivative of both sides and get whatever the antiderivative of h is whatever the antiderivative of x is, and there'll be some arbitrary constants from both sides. So using our rules, we can take the antiderivative of both sides, and because these constants are arbitrary, I can combine them into a single constant, and h of y is g of x plus some c, where c is cx minus cy. Now, why it might be a bit difficult because this is implicit, because y is not by itself. It might be difficult to get y all by itself, but at least we have some relationship that we can calculate. Now, example of something that is not separable, which looks like it should be separable, is if dy dx is x plus y. Notice it's not a product. I don't have a product of x and y. I have the sum of x and y. There's no way for me to separate it using just multiplication division, because if I move the dx to the right-hand side, I get dy is equal to x plus y dx, and that y is stuck on that side. Or if I subtract y from both sides, I get dy dx minus y equals x, and I don't have the dx on the correct side to take the antiderivative. The only thing that will work is if I have a product or a quotient of my functions of x and my functions of y to make it separable. This repeats what we had before. Now, we can have a general solution. The general solution has constants, arbitrary constants, and the number of constants equals the order of the differential equation. So if we have a second order differential equation, we'll have two constants. If we have a first order, we'll have one constant. But I might have an additional constant, given an initial condition, knowing my y value at some x value is going to be y0. So I know it goes through some point x0, y0. And that's going to give me an initial condition, which lets me find a specific problem. So let's solve this differential equation, which we had in the class yesterday, in the last video. So dy dx equals x squared over y squared. I'm going to move the y's to the right-hand side, the left-hand side, and the x's to the right-hand side. I get y squared dy equals x squared dx. Now I put the dy on the right-hand side because that's the way I'm used to seeing differentials in a integral. I'll take the antiderivative of both sides. I get 1/3 y cubed plus its own constant equals 1/3 x cubed plus its constant. Combine them into a single constant. Multiply both sides by 3. So I get y cubed is equal to x cubed plus 3 times some constant, but that's just an arbitrary constant. I'm just going to call it my new c, which looks a lot like my old c, but it's 3 times as big. So this is the general solution. And if I want to satisfy the initial condition when x equals 0, y equals 2, I'm going to plug that into the equation. 2 cubed equals 0 cubed plus c. So c is going to be 2 cubed or 8. So I get y cubed equals x cubed plus 8. All right, so let's examine that solution. Y cubed equals x cubed plus 8. So here is the slope field for dy dx is x squared over y squared. So notice when y equals 0, I'm doing x squared divided by 0. So I have an infinitely steep line. Dy dx is x squared over y squared. So when x equals 0, the slope is flat. And at different x's and y's, I get different slopes. So here is a solution for x cubed plus y cubed plus c, which is my arbitrary solution. Y cubed equals x cubed plus c. And if I want to go through the point 0, 2, when c equals 8, which you can see over on the left-hand side, it exactly goes through that point, and the slope matches x squared over y squared at any point on the curve. Now, this is an equation where we can find the we can solve for y because it's easy to take the cube root of both sides. Y is equal to the cube root of x cubed plus 8. Now, do not, if you don't want your teachers to cry or you to cry when you realize you're wrong, that is not equal to the cube root of x, which is x, cube root of x cubed, which is x, and the cube root of 8, which is 2. Those are not the same as each other, so don't write that down. You have to add the 8 before you take the cube root. All right, let's do another one. Solve differential equation dy dx equals x squared y. We do not have an initial condition, so we're going to find the general solution. We rewrite this as dy dx is x squared y, or dy over y is equal to x squared dx. On the AP exam, if you just do the separation, that's usually worth one of the points. Then we'll take the antiderivative of both sides. The antiderivative of 1 over y is a natural log of the absolute value of y. The antiderivative x squared is 1/3 x cubed plus a constant. We're going to combine the constants together. Now I have to have the absolute value because I don't know if we don't know if y is greater than 0 or y is less than 0. Because the slope still makes sense when y is a negative number, we'd have a different solution. So how I'm going to solve this, I'm going to exponentiate both sides and get the absolute value of y is equal to e to the 1/3 x cubed plus c, which using our exponent rules is e to the 1/3 x cubed times e to the c. which is some other constant, which looks a lot like the other constant, except c is now e to the c, e to the 1/3 x cubed. And so y, depending, we're going to solve for y, if y can be plus or minus, well, not just plus or minus, it can only be one of them, but it can be a negative number. So we can let c be a negative number to let c to let y also be possibly negative. So in this case, c is less than 0 if the initial value of y is less than 0. Otherwise, c will be greater than 0. And that's our general solution. All right, let's do another one. Solve this differential equation. Given that y is equal to some a value, so this is like our starting value. Y starts out at a when time is at the start when time equals 0. Notice that I'm not using x, I'm using t, because we're going to use time. This happens a lot in like biology. All right, so to separate this, the y comes over naturally to the other side. And I've got this k. K is a constant. I could bring the k along with the y, but I'm going to leave the k by itself because it's going to give a better form of the equation, dt. Notice I don't have any t's, but that's okay because I can take the antiderivative and get the natural log of the absolute value of y is equal to kt plus c. If you take the derivative of both sides of the equation, I come back with dy over y is equal to k dt. Exponentiate both sides. I get the natural log of y is equal to e to the kt plus c, or I can make that e to the c, e to the kt, or some arbitrary constant, e to the kt. Oh, I don't have natural log of y anymore. Those are gone. I just have absolute value of y. Right? So y will be plus or minus c e to the kt, or let c take the sign along with it. So when t equals 0, y is equal to a. So let's plug in t equals 0. I get a is equal to c e to the 0 k times 0, which is just 0. And e to the 0 is 1. So my arbitrary constant is a. So my initial value solution is a e to the kt. This is exponential growth. And in exponential growth, the rate at which something changes depends on how much stuff we have. So if you have if y is twice as much, the slope's twice as much. If y is 5 times as much, the slope's 5 times as much. And that's what happens in exponential growth. That's what's so special about the exponential growth function. And it goes to the point when t equals 0, y equals a. All right, here's one other one you can try yourself. This is separable because I can easily move the 2y plus cosine of y to the left side and dx to the right-hand side. Now, when you get your solution, it's going to be an implicit relation between x and y. We're not going to be able to solve. So it'll be hard to find y equals something. So won't be able to solve for y, but we'll have an implicit relationship that I can numerically solve for y given different values of x. So you can try this equation, this differential equation to solve. And there's one more you can solve, which we talked about in a previous video from the 2021 exam. There's usually a free response question using solving differential equations almost every year. And in this case, you should now be able to solve this differential equation by moving the y to the other side and get the solution, which is at the bottom. All right. We'll see you in the next video.